Okay guys, we're going to start this video out by working with something that hopefully you're pretty familiar with, and that's the absolute value of x, this function. This is the parent function, parent absolute value function, and we just want to write the definition. And so based on this definition, we know that f of x essentially has two different pieces to it, or two different parts. So the first part of it is, if we sketch a quick graph over here, we know it looks like a V, and this parent function is going to be centered on 0, 0. And so the first part of it is this part over here. And so what we start with is what x values is this particular part of this graph defined on. And so for this one, we know that these are negative x values. And so what we're going to do is we're going to say that this function, this absolute value function, is basically equal to the negative version of x if we plug in x values that are less than 0. All right, the other part of this function is the right side over here. And so we know that this is positive x. This is like y equals x. That's just a line with a slope of 1 and a y-intercept of 0. This is like y equals negative x with a negative slope of 1. And y-intercept of 0. So we've got the left side. The right side is equal to y equals x. And it's equal to that when we plug in x values that are greater than or equal to 0. So this is essentially the definition of this absolute value function. And so we're going to use this to lead into our topic for today. And our topic today is called piecewise functions. So we've got this these piecewise functions, and I just switched these two. It doesn't really matter what order you go in. But a piecewise function is essentially just a function that is defined by more than one rule. And by rule, we really mean function. So this is a particular function. It behaves like this line on a particular interval, and it behaves like this line on a different interval. So this is kind of like rule number 1. It does this when we plug in x values here, and rule number 2, it behaves like this when we plug in these x values. And so this is the big key here. It's dependent upon the input value. So what we're going to do is we're going to look at our input value. We know input values are x's, so when we pick an x, we're going to look over here, and based on this piecewise function, whatever interval x falls in, we're going to follow the rule that corresponds to that particular interval. So if our x is positive or 0, we're going to follow this rule. If our x is negative, we're going to follow this rule. So this function is completely dependent upon the input value and the interval that defines each particular function. So generally, what we have are, this is a really basic piecewise function up top, the absolute value of x. We can get into some pretty crazy ones. But the point here is that these piecewise functions are defined by numerous functions or numerous rules. So we might have one rule that's a particular function when our value falls less than a particular number or a particular input. And then we jump to a different rule when our value is a different input. So when our x is greater than or equal to a. And then we can have a bunch of different rules. So we can have 3 or 4 or 5 or infinite, maybe not infinitely many, but a bunch of different rules here. So generally, these are what piecewise functions look like. They're just defined by multiple rules based on what x value you're plugging in. So let's look at a couple of the basic things that we want to be able to do with these piecewise functions. Number 1 is evaluate. So if we're given this piecewise function up here, this is a particular example, we want to be able to look at particular x values and figure out what those x values are worth in this particular piecewise function. So if I take an input of -3, this is my input or my x value. I'm going to come up here, and I know -3 falls under this interval here, and so that tells me to use this rule. And so what I do is f of -3, I'm just going to plug it into this particular rule or this particular function. And so I plug in 2 times my input value minus 3, and this piecewise function spits out a -6 minus 3 is -9. Jump over here to the next example. I'm going to plug in a different input value. That input value is 0. And this input value happens to be, it looks like it's part of both of these intervals, but if we look at the inequality here, 0 is actually included in this interval. And so again, we're in the same interval, so we use the same rule. And so I'm going to plug in, I know f of 0, when I plug that in, I'm going to plug it into 2x minus 3, so that's equal to 2 times 0 minus 3. And so f of 0 for this piecewise function is equal to negative 3. So when we evaluate, we're just trying to find out what that particular input value is worth, or what y value corresponds to that particular input value. Let's finish these last couple up, evaluating f of 4. So 4 falls into this next interval over here. This interval, we know 4 is between 0 and 9. And so I follow this next rule, this other rule that corresponds to that particular interval. So f of 4, I'm going to plug into the square root of x, or in other words, f of 4 equals the square root of 4. And we know that square root of 4 is 2. So when I evaluate f of 4, I get 2. Last one is f of 10. That's my input value. We know that 10 follows this rule, or falls in this interval. It's greater than or equal to 9. And so this tells me to follow this rule when I have a value that's on that particular interval. So f of 10 is going to be equal to negative 2 times my input value 10 plus 12. Simplify, and we get f of 10 is equal to negative 20 plus 12 is going to be negative 8. So just to reiterate, the first and most basic thing that we want to be able to do is to evaluate different values for these piecewise functions, evaluate different inputs for these piecewise functions. Next thing that we want to take a look at is graphing. So I want to be able to take these piecewise functions and graph them. And the way that I do this is I'm going to graph these different intervals. And so the first thing I'm going to look at is I'm going to look at the first function. That's 2x minus 3. If I were to graph 2x minus 3 on a separate graph, we know it has an intercept at negative 3. And it's going to increase at a rate of 2 up 2 over 1. And so it's going to be a little bit steeper. So my graph looks something like that. Now, this particular thing, for this particular piecewise function, it only follows this graph, or this graph only looks like this thing when we're plugging in values of x less than or equal to 0. So when we plug in negative values or 0, my piecewise function is going to look like this particular graph. So what I do is I'm going to take this into consideration. I know that it's got a y-intercept of negative 3. So this is going to be actually the greatest value where this piecewise function follows this rule. And so my graph is actually going to stop there. And notice that I put a solid point here, a solid dot. And that indicates that on that point, for an x value of 0, I'm still following this rule. This is the last, it's kind of like almost like an endpoint if you want to think of it like that. But generally, it's going to look like this up until it hits 0, and then it's going to change. So I'm going to graph this just like we did over there. There's my line up until 0. It's going to continue on in the negative direction to the left and down, and follow this rule as we go more and more negative. And then when we hit 0, we're going to stop and include 0 in that particular one. So now when we get to 0, we're going to follow a different rule. Notice that 0 is not included in this particular one, but for all of the values, when I plug in a value between 0 and 9 for x, I'm going to look at the square root of x. So again, coming over here, just thinking generally about what this function looks like. This function is going to look something like that. It's going to flatten out a little bit, start at 0, 0. But for here, we don't want to start at 0, 0. So we put an open dot. And an open dot indicates that, yeah, it starts just beyond that point, and it follows that particular look, or that particular rule, until we hit the top end of our interval. So it's going to look like a square root function until we hit the top end of our interval, which is 9. And again, we're not including 9 in that, so we want to indicate that with an open dot. So there's the second part of our graph. The third part of our graph is going to follow this rule here. So from 9 all the way up to infinity, we're going to follow this rule. Quick sketch of what this rule looks like. I know that this has a y-intercept of 12, so it's going to look like this, and it's going to have a negative slope, so down 2 over 1, down 2 over 1, and so on. So our graph is going to look something like this from 9 on. And so what I need to figure out is, what does my graph look like at 9? When I plug in 9, or in other words, evaluate f of 9. So if I plug in 9, I'm going to get negative 2 times 9 plus 12. So f of 9 equals negative 18 plus 12 is going to be negative 6. And so at 9, I need to start my graph at a y value of negative 6. So I'm going to go down here. Here's negative 3. Go down all the way to, there's negative 9. There's negative 6. And at negative 6, I'm going to go ahead and, because this is greater than or equal to, I'm going to include this value. So solid dot at that point. And it's going to look like this from that point on. So it's going to have a slope of negative 2 and continue on down like that. So this would be the graph. This is what the graph of this piecewise function looks like. And we take into consideration each interval and graph accordingly. So the last main thing that we want to be able to do with these piecewise functions is we want to find domain and range of these piecewise functions. So we've evaluated for values, we've graphed this thing, and you can see I transferred this graph to this next slide here, but we want to be able to find the domain and range of these particular things. So when we go to find domain, we're looking at this graph and we're looking at these intervals, and we're asking ourselves, are there any values where we get an undefined y when we plug in an x? And so a couple different ways that you can look at this. You can look at the intervals and say, okay, this covers all the negatives and 0. And on that, under that rule, this is a line and it's continuous. So I'm never, if I plug in the negatives and 0, I'm never going to get an undefined value or an undefined y. The next one, we want to be careful because this particular function does have restricted values, and it has restricted values when we plug in negatives. So if we go over to check the interval, we're asking ourselves, we're going to get an undefined value for this function, square root of x, and we plug in a negative. Are we trying to plug in any negatives under this piecewise function? You can see that all the values on this range are going to be positive. So this is going to cover all of the x values from 0 to 9, not including 0 to 9. And therefore, we're never going to try to plug in a negative to this. So on this interval, we don't have any undefined values. The last one, we're looking on this interval. Again, this is a line, so it's going to be continuous, and it's going to be continuous on this particular interval. Last thing, check your intervals. Look at the intervals, see if it's skipping over any particular values. This covers all the negatives. This covers from and 0. This covers from just above 0 to just below 9. Non-inclusive, so we're not including these endpoints. This endpoint is included in this interval. This endpoint here is included in this interval. This is going to cover everything from 9 up. So all of the positives, so we don't have any gaps in our intervals either. So when we go to write the domain, our domain value, depending on which form you write it in, our domain value is going to be all real numbers. So I'm going to write this in set notation, all real numbers. We have no restrictions. All right, the other way that you can look at this and find domain is look on the graph and see if anything, this is going to continue all the way to the left. So there are no values from here to the left that are not going to be included, that aren't going to spit out a y value. In between here, in this next interval, we've got all of these values covered because the graph, there's no breaks in the graph. And so all of those domain values are going to return an output value or a range value. And then once it stops here, we skip right down to here. And this thing is going to be continuous as well. And so that tells me that there are no domain values that, that are going to return an imaginary number or a non-real solution. Okay, the next part we're going to look at our range values. So let's check out our range, look at all of our y's. When we look at our y's, we see that this thing goes all the way down in two different spots. So everything basically from this point down is going to be covered. So we're good there. From here, we've got a break in the graph, and this particular break in the graph is going to represent a range restriction. So these are values where it doesn't matter what x we plug in, we're never going to get a range value that's between 0 and -3. All right? So that's going to represent a range restriction. We want to make sure that we take those out of our range when we report it. The other thing is this thing does not continue all the way up or all the way in the positive direction past this point. So this is another breaking point. Everything up from here is not going to be included. So this is another range restriction. Or in other words, these are values from this point up that we don't want to include. So when I go to write my range, I want to write what values do work, what values I do have on my graph. So I want to make sure that I exclude these restrictions. So my range is going to look like this. If you write it in set notation, I'm talking about y's when I talk about range. So all of the real number y values such that y is not between these two and it's not bigger than this. Well, the other way to say that is I've got all of these values. This is a value of 3 and -3 and -3 is included. So all of the x's that are less than or equal to -3 are a part of my range. And it skips this little spot, and then all of these values I'm always going to have a range value. So whatever I plug in, I'm always going to have something that's either down here or in here. That's what our range, that's what we want to represent. So how do we represent in between two values? Well, 0 is my value here, and that's going to be strictly less than, because we can't get a 0 out of that. And these are, I'm sorry, I should have used a y right here. It should be a y. So my y's are going to be between 0 and 3 on this interval. And we're not going to include 0 or 3. And so my range actually stops there. So there's my range for this particular piecewise function.